All right, hi everybody. Let's get started with today's lecture. So I was asked by Ryan to remind you all that the homework is due on Thursday. Shiva will be giving a lecture on SDP relaxations on Thursday. Wu Young also has her recitation on Wednesday, which is an advanced topic recitation on MCMC. Also, if you haven't filled out the course evaluations, and you haven't, then you should go turn them in. So please remember to do that. So today's lecture, I'll be talking about dual averaging, which is a subgradient method that can be thought of as an extension to subgradient descent. It was invented by Nesterov about 2007. Unlike his acceleration, there's actually some nice insight here that I think we can all understand. So let's get started with that. So to start off, I'm going to be motivating dual averaging by going over the subgradient method. So this is something that we looked at in the beginning of the course, something like lecture 6. So if we remember, for the subgradient method here, we have some convex function f, and we have some sequence of decreasing step sizes, and we just take a subgradient at our current point, and then we just take a step along that subgradient. So this should all be familiar to everyone, right? Pretty straightforward. So for the convergence of the subgradient method, we had, I'm not going to go over the proof again, but we had something that looked kind of like this, where we had, is this, oh, I don't have a pointer. Okay. So we talked about using the best thing that we've seen so far, right? So we just remember the best iterate so far. And we showed that converged so long as you chose the step sizes correctly. So the step sizes had to be chosen such that this bound on the right-hand side is decreasing. Another thing that we didn't discuss, which is also quite important, is that the average iterate, where you average the iterates according to their step sizes, also converges. So why is this important? Well, sometimes you can't actually evaluate your function exactly. So for example, if we're doing stochastic optimization, we would only have an estimate there of the function value, not the actual function value. So we can't just take the best iterate, right? But in this case, we can still just keep the average function value. And so if we're doing stochastic optimization, we can also converge to the optimum in that case. Does that make sense to everybody? Right? So for now, we're just going to be talking about this average iterate. But keep in mind that if you can evaluate the function exactly, you could use the best iterate as well. Right? So an artifact of the proof that the subgradient method worked was that we had to choose our step sizes according to this divergent step size rule. Just to clarify, if we knew how many iterations we were using in advance, we could pick a constant step size, which was in proportion to sort of 1 over the square root of the number of step sizes. But if we don't know how long we're going to run our algorithm for, we have to choose our step sizes such that the denominator here goes to infinity, but the numerator does not, right? So we need sort of the square of this series to converge, and we need the series itself to diverge of step sizes. Does that make sense to people? Do people remember this from the beginning? Right, so it's pretty clear here that if any sequence of step sizes that makes this bound go to 0 is something that we'd like. So for example, if we take 1 over square root k as our step size, then the rate that we get the convergence here is log k over square root k. So we'll see this come up later, but you actually pay a log k price here for not knowing exactly how many iterates you're going to run for. Another thing that we did discuss earlier, but I'm going to gloss over for the point of this lecture, is you actually do want to choose this step size in proportion to the Lipschitz constant of your function. And if you know how far away you are from the optimum, you can take that into account as well, right? So those are better step sizes in terms of like the actual bound you get, but not in terms of the rate. Does that make sense to people? Yeah. So here we're talking about we're talking about subgradients, right? So the function is not necessarily smooth. So in this case, you have to use 1 over square root k. So if your function is smooth, then you could use, or strongly convex, you could use 1 over k. Yeah. Yeah, Addy?
Yeah. Get log k by root k, but it's not
do you want it in terms of epsilon? So if it's in terms of epsilon, you have 1 over epsilon squared there.
It doesn't satisfy that, but it's the right rate, and that's what we get for the rate.
You sure it doesn't satisfy this?
Yeah, but so there are different, it doesn't satisfy what you wrote down, but that's also valid satisfies for convergence. There are other kind of sufficient conditions for convergence that we talked about. Taking 1 over k would satisfy the two.
I see. Interesting.
But you still get log k by root k.
Yeah, the rate's fine. All right, I'm a bit confused, but we can just move on. So anyway, yeah, like I said, we have two terms here for this divergent step size rule. One for the numerator, one for the denominator. That's okay, though, because I think the rest of this will still all make sense. So let's take a closer look here at what the subgradient method's actually doing. So I'm going to just start doing some math here, and trust me, it'll all make sense in the end. So remember that we can write the subgradient update as this this particular minimization. That's not magic to anyone, I assume, right? You just write out this minimization here, right? So if x k plus 1 is going to be the argmin over x of the linearization of our function at xk. X minus xk. And then we have this quadratic regularization term here that takes into effect the step size, right? So if we just differentiate that, set it equal to 0, and solve for x, we get exactly our update rule that xk plus 1 is equal to xk minus tk times the gradient, right? So everyone's okay with that? Is that too small for people? There. All right, so let's do some rearranging here. So the first thing that I want to do is multiply through by this step size. All right, so we'll just throw this tk up like this. And we'll also throw away, for now, this term here. The minimization doesn't depend on that term, so we'll just ignore that for now. Right? And then we've got the regularization term here, squared over 2. Okay, so now what we want to do is expand xk in the regularization term. xk plus gk dot x plus x. So now we know that xk, based on this recurrence here, is going to be xk minus 1 minus the previous step size. And then the previous gradient. All right. So now we can expand out this norm. Right, so we're going to get a xtx over 2 term here, right? That comes from this guy here. And then we'll get a term that looks like xt times what's in the brackets here, right? And there's going to be two of those, right? So that's xk minus 1 minus tk minus 1 gk. Right, and I'm just going to ignore this cross term with itself, because again, that doesn't depend on x, which is the argument. Right? So now if we do this forever and ever and ever, right, until we get down to x0, what we can end up doing is we see here that, let's look at what the terms are going to be here, right? So technically speaking, this term doesn't matter for the minimization, right? So we have tk times the kth gradient times x, right? We have tk minus 1 times the gradient k minus 1 times x, right? Let's just assume that we started at 0, so this term is just going to be 0 at the end of the day, right? And then we'll have this quadratic regularization term, which has no tk, right? So, and now I'm going to make it look like what I have on the slide, I'm going to throw back in these terms here, which again, the minimization doesn't depend on, so I'm allowed to do that, right? So I can just sum over all the iterates, I to k, tk times fk plus g. Oh, this is an I. So x minus xi plus this quadratic term. Everyone's okay with that? We didn't do anything too fancy, right? And now I can just divide through by what I've called zk here, where zk is just the sum of these step sizes. And remember, since the step sizes are positive, that this is a positive number, so I'm allowed to do this. So this algebra is all fine with everyone? Here? There? All right. Okay, so we did all that math. Why should we care? Right? So this is what Nesterov noticed. We see that the step size in the way that we've written this minimization come into play in two different places. Okay, so just to pick a different color here. Right, we have a step size coming in to effect here as well as here. Right? So now recall from the definition of a subgradient, right? We have, for all the points we've evaluated the function, right? We have f of x is greater than or equal to the linearization at that point, right? This is just the definition of a subgradient, right? So we can take any linear combination of these constraints and come up with a lower bound on our function, right? So in particular, if I take any lambda i's that sum to 1 and that are greater than 0, then I know that f of x is greater than or equal to the sum of those constraints, right? So if we look what's happening here, essentially what's happening is the subgradient method is minimizing the sum of a lower bound on our function and this regularization term, right? And so Nesterov says, why should this lower bound, in this lower bound, why are we weighting the subgradients differently, right? Like, in particular, we're actually taking the newest subgradients and we're giving them smaller weight. And we have to do this in order to get convergence, right? That was what the decreasing, the divergent step size rule said, right? So in order to get convergence for the subgradient method, we're actually making less use of the most recent information. And this was something that was necessary. So this is sort of the whole point of the lecture right here. So if you don't get it, you should ask a question. Okay, right? So all Nesterov is going to do is introduce another sequence of parameters, one here for the subgradients, and a second one here for this regularization term. All right? So that's exactly what he does with dual averaging. So he has a bunch of schemes that he mentions in his paper, but the simplest one is to just weight all the subgradients equally. Right? A subgradient's a subgradient, so we'll just weight them all equally. And then we have this mu term here, which controls the step size. So this, this zk term here, it's on the order. It's on the order of 1 over square root k, I think. Did I get that right? Did I get it wrong? I think that's right. So we'd expect this second sequence here, this mu k over k, to be something of this right here, which is what we'll see later, right? So you can see here that I've written the minimization in two forms. So in the first form, we actually have this explicit representation where we're taking the average of all the subgradients so far. But when you're actually coding up the algorithm, you just actually explicitly encode the average subgradient you've seen, right? So you don't actually have to keep around every single individual subgradient, right? Okay. Right, so we have a step size control here, and then we have that the subgradients are now equally important, whereas in the subgradient method, we didn't like the new ones for some reason, right? So here's what the algorithm looks like if you run it as I've stated, right? So this is pretty straightforward, but I'll just write it out anyway, right? So we had, we wanted to find the argmin, so we said x t plus 1, right? So we had this hat plus mu k over 2k, right? So you just get mu k over k x equals negative gk hat, right? So that's where that update rule comes from. Yeah? Oh, I'm sorry. There we go. Right, so yeah, that's really the only difference. You just start off at the 0 subgradient instead of starting at, say, 0, right? And then you just compute your iterate x using this rule, and then you compute the next subgradient. So one thing that might look funny to you here, and I mean this is kind of the point, is you're not really taking a step from your current iterate, right? So this sort of has a little bit of a flavor of like the acceleration that we saw, where you have like a query point, and you sort of get a subgradient from that, and then you choose a new query point. And they do have a relation to one another, but you're not really sort of looking at the function locally from that query point in a sense, right? Right, so the proof is just like the same as all these other proofs. There's nothing really to take from it, so we'll just skip it. And I'll just show you the convergence rate. So if we set mu k to be order root k, then we get convergence that looks very similar to the subgradient method. You actually do get the benefit here where we've lost that log k factor from the rate. So if that's really important to you, then amazing, but whatever, log k. So the other thing here is, again, with these step sizes, you can do things if you know an estimate about how far away you are from optimum and the Lipschitz bound on the function. So if you have those, you can change the step size accordingly, and you can just look in the paper for how to do that. And one thing to note here, the thing that you will return is just the average of the query points that you've seen so far, right? And here we're using just the normal average. We're not using any sort of weighted average by the step sizes, right? So each iterate is just as important as the last one. Okay, so here's the algorithm. Does anyone have any questions about sort of the motivation or what it's actually doing? Okay, so there is a couple cool things about this algorithm that we have over the subgradient method. So one of them was we lost that log k in the convergence rate. The second thing, this is where sort of the dual comes in dual averaging, is this method is primal dual in the sense that we're keeping two sequences of parameters. We're keeping this x, the average of the x's, and we're keeping these g's, which are the average of the gradients. And there's a particular primal dual problem that we're solving. So I'm going to show you now what that is. And that'll actually be a little bit advantageous for us. So I'll just derive the dual here that I have written out on the slide. So remember here that our function f of x, it's convex, so it is the conjugate of its conjugate, right? So we can just simply write it as the max over g of g minus the conjugate of, right? So far, there's nothing magical here, right? So if we're trying to minimize f of x, we could just simply minimize this here. G. And now to sort of make the dual problem sort of interesting, we're going to put a bound here on x. So we'll just put a norm bound on it. And remember, this d is the magical thing that we think we know how to get. We can talk about that later, right? And so now, assuming that strong duality holds, that means we picked d large enough, right? We can just simply write this here, max g min x d. Right? So now the conjugate here doesn't depend on this minimization, so we can bring that outside. Max g. Right? And then this here is just the support function. So if we do a change of variables, if we basically take this d here and replace x with dy, say, right? Then I can basically multiply this by d and turn this into the dual norm. Should I write that out for people? Okay. So right? And then this comes outside, and this is now just the dual norm of G, right? Did I mess something up? Well, I haven't got the answer yet. Yeah, so, okay, I think what you're saying is we want to change this to a min, right? And then I throw the minuses through, right?
I think that the definition of zero is minus.
Oh, yeah, sorry.
Minus of a minus
Shh,
and then
shh.
minus minus.
That's where this comes from. Yeah. And then I can change this into a min if I want. All right. I can't do algebra, apparently. All right. So at the end of the day, remember that this was f of x, right? So if we subtract these two things, then we should get 0. Let me see. Did I miss a sign again?
Yeah, there's a minus outside the min in the last line.
Yeah, there we go. Right? So if we subtract these things, assuming that strong duality exists, we get 0. Right? So that's where the dual comes from here on this slide. Right? So it is a little weird because we have to know this bound D on how far away from optimum we are for this to be a valid dual. But reminder, you need that D in the subgradient method to actually compute your bound on how close to optimal you are, right? So it's not too much of a stretch here to ask you to know this D. The cool part about this, though, is this is essentially a duality gap that we can actually measure, right? And dual averaging the values, average x and average g, approach optimality for this primal dual problem. So whereas in the subgradient method, all we had was a bound typically on optimality, here we actually have a dual problem that we can measure how close to optimal we are, given that we know D. Does that make sense to people? Right. I guess it's assuming that we have the conjugate, so we can evaluate the conjugate as well. Right. So here's yeah.
Why can you choose these
So right here, like, why can I do that? My problem is convex, and I'm assuming that D is large enough so that